Welcome to another in the set of videos describing the practical nature of control systems. In this video, we'll look at the two basic types of control loops that are found in industry nowadays, a positioner versus a regulator. And as we shall see, the aim of each one of these loops and the way that it operates is quite different. As our starting point, let's look at the control loop as we originally defined it. The components in the control loop are being described conceptually, and how these components fit together to make a feedback control loop where the actual value, what we have, is equal to the desired value, what we want. So we started with this conceptual rendition of the loop in an earlier video, and we then abbreviated it by giving the various components of variable names where the subscript reflects what component that belongs to. And then also, additionally, we have given names to the signals that travel between components in the control loop. This represents the flow of information in the control loop, and they have specific names and variable names. R is the reference value, E is the error, the deviation between the actual value and the desired value. The command value from the controller is U, which tells the actuator to do something. F is the force imposed by the actuator onto the plant. And C is the actual value. We have a sensor down here, H, and B is the measured value. So we'll start off with a loop in equilibrium. Everything is zero. Basically, the desired value is zero, and the output value, the actual value, is zero. So we're happy with the way this loop is operating because what we have is what we want. And as we can see, the sense value is also zero. It's just a reflection of the actual value. And when we compare the desired value with the measured value, we wind up with zero error, which goes into the controller. The controller receiving a zero, that's a message basically to do nothing. And so it does nothing. It sends a signal, basically do nothing, to the actuator, and the actuator responds by not doing anything. And so the system just continues to sit at whatever state, at this equilibrium state. The message inside the loop from one component to another, from every component to the one that it's connected with downstream, is basically don't do anything. What happens in a positioner loop is that the operator of the system that has the control loop in it makes a change. So as you can see here, the operator decides to make a step change from wherever, from the desired value that existed prior to the change to a new value. And this is called a unit step input. And as we can see, what happens is that the new desired value is then not equal to the measured value, and that generates an error that's non-zero. Non-zero input to the controller basically tells the controller to do something. So now the controller does something and will produce an output signal, a command value or command signal to the actuator to basically do something. So basically what happens here, we started off in a situation with the input being changed, a step change being made, and then that non-zero value being propagated through the loop, starting with R and then finding its way around the loop. As was stated, the non-zero signal to the controller means do something, and the loop will spring into action and try to move the actual value to the new desired input value. So we're changing equilibrium states is what we're doing here, and the job of the controller is to move the plant, the system that we're controlling to a new equilibrium state. A positioner also has other names, and it's known, for example, as a tracker. That's because the job of the loop is actually to track a changed input value. So you can change the input value over and over again from one point to another point depending upon what you're trying to do. Move a mass around at various points in some type of automation cycle, or for instance to move the altitude of an airplane from one altitude to another altitude and then maybe to another altitude. So it's called a tracker because the job of the loop is to make the output value track the input value. It's also known as a fly-by-wire system because of its use in airplanes. Fly-by-wire alludes to the fact that in an airplane, well, it's in an airplane, so we use the word fly, which is where this type of loop was developed. And the connection between the output from the controller and the actuator is not a mechanical linkage. It's actually an electrical signal and an electrical wire. So the name developed fly-by-wire when these control loops were developed in the late 1940s and the early 1950s. The defining characteristic of a positioner loop is that the desired input value changes regularly as the operator of the loop moves the system that's being controlled from one equilibrium point to another equilibrium point at specific points in time. Now let's look at a regulator, a different type of loop. And what we'll notice first is that there's actually an additional element here between the actuator and the positioner, a summing block with the entry of a second input into the loop called the disturbance. Notice that in this case, well, as we shall see, we do not change the desired value. The desired value stays where it originally was, but then a disturbance comes into the loop, a non-zero disturbance comes into the loop and knocks the actual value away from the desired value that it originally had. The disturbance, as well, this states what I just said, comes into the loop, and actually the loop previously every signal was also at zero, so we were in the do-nothing state with every component telling every other component not to do anything. But then all of a sudden a disturbance comes in and upsets its equilibrium. If all of the signals in the internal part of the loop were 0 before, and then we input a non-zero signal here, it's fairly obvious to see that F will now change and become a non-zero value, and then that will tend to make the non-zero values propagate around the loop. So F becomes a do-something signal to the plant, and the plant moves away from the equilibrium point that it had where it had operated before. Now the job of the controller is actually to bring the actual value back into alignment with the desired value. Let's look at how this works. Disturbance affects the plant and drives the actual value away from its previous operating point as stated. It can come in as either a positive disturbance or a negative disturbance. It depends on the existing situation, as we shall see. Now we have this do something signal going into the plant. And as stated before, it's the job of the control loop to bring the actual value back in line with the desired value. Now we can actually also rework this loop using something called block diagram algebra. We want to emphasize the fact that the input to the loop that's upsetting it is the disturbance, not a change in the input value. In fact, as can be seen here, all we've done is we've redrawn the loop. All of the internal components of the controller are still connected to one another as they had been before. But now we have a non-zero excitation coming in, which is our disturbance, and we're still interested in the actual value. That's the value of interest to us, but we've reworked the loop to emphasize the fact that the desired value is the exciting value for the loop. What we've done here also in this case, this is a further development of the loop. Since we were adding in the desired value as a 0 and we continue for that to be our desired value, we're not adding anything into the loop at that point. So we can actually get rid of the comparator, the block that compares the desired value with the measured value. And so the desired value is equal to the measured value. But in the original loop, when this signal came through here and entered the comparator, there's a sign change for B. So if B had been 1, when it comes into the comparator, it becomes -1. And we have to preserve that action. It doesn't look like we preserve that action here, but if you look carefully at this loop, originally, the original loop just simply redrawn has the signal from the actuator entering the disturbance summing block as a positive. And all that we've done here is we have moved that negative sign downstream and actually changed the flip-flopping of signs from the comparator to the disturbance summing block. So we've actually preserved the system in the original state. Now E is equal to B. We've taken R out because it's 0, and we've moved that sign downstream as was described previously. What we just did is called block diagram algebra. So we can get a block and we can change the configuration of it, but we have to preserve the relationship that we had prior to the change and reflect that in the new block, so that, or the new configuration, so that the new configuration is equivalent to the previous configuration. And this is very similar to redrawing circuit diagrams in electrical engineering. You can't just change things willy-nilly. You have to preserve the existing relationships between the components in that electrical circuit, but you can redraw the system to emphasize a certain point or to make actually the function of the system perhaps more clearly to someone who is looking at that diagram. Why do we want to emphasize that D is the input? Well, we may not be easy to describe that at present, but let's just leave it at this, that in block diagrams it's very important to, the input and the output are very important, and there is a rationale for wanting to emphasize what the input is to the block and what the output is to the block, what the cause is and what the effect is, basically. I'd like to also describe the fact that all of this information in these videos is contained in a book that I've written about the subject, a very practical approach to control systems engineering, and it's available from PolyX Engineering for $25 plus shipping and handling. If you'd like to order a copy of this book, please send me an email at fon@polyxengineering.com. Thank you for your attention, and I'll see you in the next video.